sorry. Okay. Oh, sorry. I actually got to know Shoucheng most in 2010 and 2011 when we visited Stanford for a number of months. And I had a lot of discussions with Shoucheng, also a lot with Xiaoyang. And I was extremely impressed with Shoucheng's insights and his enthusiasm, the breadth of his interests. And at the end of the period, actually, the three of us wrote a paper together. So it's an honor to be invited to talk here. And I'm going to be talking about a problem in string theory, but I'll try to explain it in a way that requires no prior background in string theory or no familiarity with D-Branes. In about the last 3 minutes, I'll say one or two things that will be clear if you do have some string theory background. But until then, I'll put it in the context of things that will be familiar to most of you in this audience. So supersymmetric D-Branes have been important in string theory for a long time. And a few years later, Ashok Sen showed that non-supersymmetric D-Branes are also important. And they have subtle properties that were nicely elucidated by Sen. And there was also work done later by Krauss and Larson, which is relevant to my talk, but which I won't have time to explain what they did. Now, because time will be short, I'm only going to explain the most basic case where the anomaly that drives the story is a mod 2 anomaly. This is analogous to the Kitaev fermion chain without time reversal symmetry. And in string theory, it's relevant to type 2 superstrings. So if we include time reversal symmetry, we would get type 1 superstrings and a mod 8 anomaly, just as in the time reversal invariant version of the fermion chain. So actually, Sen showed that these string theory applications are most significant in the T invariant case. But for today, we'll only have time for the basic picture without time reversal symmetry. So the story revolves around a certain mod 2 anomaly, which is simplest to see in space-time dimension 1, which means zero space in one time dimension. In other words, ordinary quantum mechanics, where you have a quantum system that, if you like, is defined at a point, but it's just a quantum system that evolves in time. So if we do a path integral, it'll be a path integral on a 1 manifold. And topology is simple, since, for example, a compact 1 manifold is going to be a circle. Once when I made this assertion, a mathematician in the audience corrected me and said, a compact connected 1 manifold will be a circle. Unfortunately, okay. There are two spin structures on the circle, which means the following. A fermion field lambda on the circle could be either periodic or anti-periodic in going around the circle. So in one dimension, one space-time dimension, there's only one gamma matrix. Its square is 1, so it can be the number 1. And therefore, a fermion doesn't have to carry any indices. There are no Lorentz indices. It's just a one-component real fermion lambda. But it can still, because it's a fermion, be either periodic or anti-periodic in going around the circle. So in string theory, these are called the Riemann and Short spin structures. So the path integral with anti-periodic fermions on a circle of circumference beta in a theory with the Hamiltonian H computes the thermal partition function trace e to the minus beta h. While if the fermions are periodic, you get the same trace, but with an insertion of the operator minus 1 to the f that distinguishes bosons from fermions. So I think it's well known that twisting the fermions by an extra sign will insert this operator minus 1 to the f that counts fermions mod 2. But I think it's well known that which spin structure comes with the minus 1 to the f operator is opposite from what you might naively think. Now, let's do the path integral for a fermion, a one-component real fermion, in the Riemann spin structure, which means that the fermion obeys periodic boundary conditions. Well, the Dirac equation just says that the lambda dt is 0. There are no gamma matrices. And if lambda is allowed to be a periodic function on the circle, then it can have a 0 mode. Just a constant mode of lambda going around the circle. A constant, lambda equals 1, is a 0 mode. A fermion path integral with a zero mode is trying to produce a non-zero value of the expectation value of the fermion operator. But a non-zero value of a fermion operator violates the symmetry -1 to the f, which is fundamental in all areas of physics. So this is inherently an anomaly. It violates -1 to the f symmetry. Related to this, although lambda has a one-dimensional space of zero modes, there's no natural choice of sign for the measure for integration over this mode. So there's no way to make sense of the sign of the non-zero matrix element, the expectation value of lambda. Any procedure that would tell us what the sign should be would explicitly violate the -1 to the f symmetry. Now, by contrast, if the fermion is anti-periodic in going around the circle, there's no zero mode, and there's no problem in defining the path integral, which has a well-defined value. However, there's something problematical with the value. The numerical value of the path integral is the square root of 2. And, okay, see. For a single real fermion, you can't add a mass term by Fermi statistics. So the Hamiltonian is 0. So since the Hamiltonian is 0, the trace of e to the minus beta h is just the dimension of the Hilbert space. So there's a problem because the square root of 2 isn't an integer. You can compute the square root of 2 using zeta function regularization, but a more physical way to do it, gosh, I didn't write this, I think. A more physical way to compute that number, here. A more physical way to proceed, suppose we take 2 copies of this system. Then in the Ramon spin structure, there are an even number of fermion zero modes, so there's no anomaly. So with an even number, there's no anomaly because the number of zero modes is even. So that's our first example of a mod 2 anomaly. What I think I didn't write on the slides, apparently, is that with 2 copies, you can quantize in the Nevers-Schwartz sector. The lambdas become gamma matrices. The Hilbert space has dimension 2. And so the path integral equals 2. So with 1 fermion, it must equal the square root of 2, which is also the answer you'll get from zeta function regularization of the determinant. So it's a well-defined path integral, but it doesn't have a sensible Hilbert space interpretation. So that's a kind of problem again. Anyway, the fact that there's no anomaly with an even number makes this our first example of a mod 2 anomaly. Now, in this mostly condensed matter audience, probably most of you know one thing we can do with this anomaly. We consider our 0 plus 1 dimensional system to exist on the boundary of a 1 plus 1 dimensional world on which there's a gapped but topologically non-trivial system. And this gap system is a gapped chain of Majorana fermions introduced by Kitaev. But I'm going to describe this system in a somewhat abstract relativistic language. So to describe fermions on a 2 manifold that might be curved or topologically non-trivial, you need something which is called a spin structure, which tells us that sign you get when a spin half field is parallel transported around a non-contractible loop. You see, if you have an integer spin field, Riemannian geometry tells you how to do parallel transport around any loop. The factor for parallel transport of spin half is supposed to be the square root of the parallel transport of spin 1. But you have to decide on the sign of the square root. If a loop is contractible, if it can be shrunk to a point, you determine the sign by saying that the point loop has parallel transport 1. But if you go around a non-contractible loop, there's no physical principle that tells you the sign of the square root. And a spin structure is a choice of those signs. So for example, in the case of a torus, which I've drawn, there are 2 times 2, which are 4 spin structures, because we need a sign of the square root going this way, and also a sign of the square root going this way. Now, on a 2 manifold with a spin structure, there's an important mod 2 topological invariant that I'll call zeta. To define it, we'll consider a positive chirality fermion field chi on the surface sigma. So we can write an action for such a field. And the only thing we're going to need to know is that we can write an action. And since we can write an action, and this is a fermion field, the action is an anti-symmetric matrix. Well, it's an anti-symmetric matrix acting on a field, so it's an infinite rank anti-symmetric matrix. But it's anti-symmetric by Fermi statistics. Here's the canonical form of an anti-symmetric matrix. It has non-zero modes that come in pairs because there are 2 by 2 blocks, and it has zero modes that are not necessarily paired. So the number of zero modes can change only when one of the so-called skew eigenvalues A, B, and so on becomes 0 or not 0. And when that happens, the number of zero modes jumps by 2. So the number of zero modes mod 2 is a topological invariant, which is called the mod 2 index of Atiyah and Singer. So that's what I call zeta. So for example, let's go back to our Riemann surface of genus 1, which I've now drawn differently as a parallelogram with opposite sides identified. The Dirac operator for a chiral fermion is just d by dz bar. So a solution of the Dirac equation is a holomorphic function. If you allow it to be periodic in both dimensions, you can have a holomorphic function without a pole, namely a constant. But if you don't allow it to be periodic in both dimensions, it will have to have a pole. So there's one solution of the Dirac equation in the plus-plus spin structure. Well, I should have said that. There are 4 spin structures, usually labeled by their signs, going around the 2 directions. So plus-plus means periodic in both directions. In that spin structure, there's one solution of the Dirac equation, and therefore zeta is 1. For the other spin structure, zeta is 0. So the plus-plus spin structure has a single zero mode, the constant mode. The others have none. So zeta is 1 for the plus-plus spin structure and otherwise 0. Now, there's a fermionic SPT phase with no symmetry except -1 to the f, in which the partition function on an oriented 2-manifold is -1 to the zeta. How do you know that's true? Well, you could give an abstract proof by showing that zeta obeys the right axioms, but you can also give a concrete physical realization, which is what I'll do in a moment, and will also be more familiar in condensed matter. So there is such a phase on a 2-manifold without boundary, but on a 2-manifold with boundary, there's a problem. And there's a reason there's a problem is that we use the chiral Dirac operator to define zeta. There's no problem to put a boundary condition on the non-chiral Dirac operator, but there is a problem for the chiral Dirac operator. The reason is that when a chiral fermion meets the boundary, it's naturally reflected back with opposite chirality. So there isn't a sensible boundary condition on a on a chiral fermion. And since we define zeta by counting the zero modes of a chiral fermion, we can't define zeta as a topological invariant when there's a boundary. So -1 to the zeta has a problem when there's a boundary. And that will link us up to the anomalous boundary state we had a moment ago. So the SPT phase with partition function -1 to the zeta doesn't make sense on a manifold with boundary if the boundary is supposed to be trivial. But it turns out it does make sense if the boundary has the anomalous 0 plus 1 dimensional theory we started with. So here's a 2-manifold with boundary. And let lambda be a real fermion on the boundary. And let D be the corresponding 0 plus 1 dimensional Dirac operator. And since the only gamma matrix is 1, the Dirac operator is just d by dt, where t is the time. The d is just the time derivative on the boundary. So the path integral of a real fermion is formally the Pfaffian of the Dirac operator. If you don't like Pfaffians, you can call it the square root of the determinant. And although the Pfaffian and -1 to the zeta don't make sense separately in this situation, the product is well defined. So the product describes a system which in the bulk is our SPT phase, and on the boundary, it's got this anomalous fermion system. Now, one way to see this is to construct an explicit gap system whose partition function is -1 to the zeta, and see how it behaves on a manifold with boundary. So the most obvious gap system of fermions in 2 dimensions with no extra symmetry is a massive Majorana fermion psi, whose Dirac equation is d slash plus m, psi equals 0. I have to warn you, I'm going to cut a corner to enable a simple explanation. A prize later to anyone who spots where I cut a corner. So formally, the path integral is the Pfaffian, or the square root of the determinant of d slash plus m. So that's real because the Dirac operator is real, but we should ask if there's a subtlety in defining its sign. So in general, there is, and we want to make sure that we start with something well-defined. So I'll get something well-defined. I want to start with the starting point that I know is completely well-defined and anomaly-free. And to do that, I'll simply take two copies of the real fermion. So I take two identical Majorana fermions, psi 1 and psi 2, with the same mass m. Then the path integral is now the square of the Pfaffian. So it's the square of the real number, so it's positive. So now it's positive and therefore anomaly-free. Anomalies always involve the phase of the path integral. And since it's a gap system, it's in condensed matter language, the path integral will be trivial at long distance. At long distance, all we'll get will be non-universal terms that we can remove by uninteresting counterterms. Well, I said that in a mixture of condensed matter and relativistic language. Now, in condensed matter, you would not usually add this second fermion to get a well-defined system. You'd start with a band structure which somewhere had a light fermion. And relativistically, the momentum dispersion relation goes off to infinity, but in band theory, it would somehow be compactified. So in band theory, your one Majorana fermion would be regularized by the rest of the bands, and you wouldn't introduce a second one to regularize it. In relativistic language, I don't have the rest of the bands, and I don't have a compact momentum space. So instead, I add a second Majorana fermion. The way you can imagine it is that you've got two dispersion relations that go way, way off into the sky, where somebody glued them together to compactify it. So that's a relativistic analog of band theory. But anyway, either way, we want to start with something which we know is well-defined and trivial, and then we'll tamper with the system and see what happens. Now, to get something more interesting, we're going to flip the sign of the mass of one of the two fermions, let's say psi 1. Now, so now the mass parameter in the Dirac operator is minus m for psi 1 and plus m for psi 2. It doesn't matter which sign we take for m because 1 is positive and 1 is negative. To get from one theory to the other, you can make a chiral rotation of one of the two fermions, which would flip the sign of the mass parameter in the Dirac equation. So a relativistic physicist would say naively the mass parameter doesn't matter because the physical mass is the absolute value of the mass parameter in the Dirac equation. That's because you can flip the sign of the mass parameter with this chiral rotation. Now the chiral rotation acts as +1 on modes of psi 1 of positive chirality and -1 on modes of negative chirality. So it might change the sign of the path integral measure. To decide if it does, we have to decide if the number of negative chirality modes is even or odd. Because we're going to get a -1 for every negative chirality mode. Since this chiral rotation transforms the path integral measure by a factor of -1 for every negative chirality mode of psi 1. Now, the non-zero modes of the Dirac operator come in pairs because of an analog of Kramer's doubling. So there are an even number of non-zero modes. It's somewhat analogous to the doubling I had at the beginning because the operator was anti-symmetric. But anyway, the non-zero modes come in pairs and they don't contribute to the anomaly. That's actually a universal fact about fermion path integrals. Non-zero modes never contribute to anomalies. So the anomaly only comes from the zero modes. And the number of negative chirality zero modes is by definition equal to zeta mod 2. So a factor of -1 for every negative chirality mode means that this chiral transformation multiplies the partition function by -1 to the zeta. So in other words, under our chiral rotation, the path integral measure for the zero modes picks up this factor, -1 to the zeta. So the theory with two otherwise identical Majorana fermions with opposite signs of the mass, it's not equivalent to the theory with the same sign of the mass. Rather, it gives a physical realization of a theory in the SPT phase with partition function minus 1 to the zeta. But now let's consider what happens on a manifold with boundary. Well, we need a boundary condition. But now we're studying non-chiral Dirac operators, so boundary conditions are possible. And here are two equally good boundary conditions, which are that if n is the normal vector to the boundary and n slash is gamma dot n, I say that n slash of psi on the boundary is either plus psi or minus psi. Those are two equally good boundary conditions, and they actually are exchanged by the chiral reflection. So n slash reverses chirality. So as I said some time ago, for a non-chiral Dirac operator, you can make a boundary condition, but the boundary condition mixes the two chiralities. So to make sure the boundary condition introduces no anomaly, we use the same boundary condition for both psi1 and psi2, so they are still identical, and the path integral is still, if they have the same mass, is still the square of a real number. So as long as the two fermions have the same sign of the mass, we still have a completely trivial theory with its path integral being the square of a real number, the Pfaffian. Now we consider the interesting case that the two fermions have equal and opposite masses m and minus m. So anomalies can depend on the boundary conditions. This might be slightly unfamiliar in condensed matter, but it's a general fact. A fact which I think is more likely to be familiar, or more universally familiar, is that anomalies don't depend on masses. So if the two fermions were identical with the same mass, the theory is anomaly-free and trivial. If they're identical except for different masses, the theory is still anomaly-free, but it might be more interesting. So let's look at the Dirac equation, which now takes this form explicitly in terms of coordinates x1 and x2. And I'm going to look at this equation on a half space. So I hope you can read this notation. So x1 runs this way, x2 runs vertically. The gray is the half space where we're studying the Dirac equation. The black line is the boundary. And we're going to look for a mode of the two-dimensional Dirac equation that's localized along the boundary. So we look for a mode that's independent of x2 and on a flat half space. So the equation reduces to a one-dimensional Dirac equation that was essentially first studied by Jakiv and Rebbe about 45 years ago. And since it's a one-dimensional Dirac equation, we can easily solve it. Here's the solution. And if the boundary condition is that gamma 1 times psi on the boundary is plus or minus 1 times psi, or I call the plus or minus 1 sign epsilon, then the solution is explicitly like this. And that's localized along the boundary if and only if m epsilon is positive. Now for the trivial theory, psi1 and psi2 have the same sign of m, so no matter what we choose for epsilon, the number of boundary localized modes is either 0 or 2, which is an anomaly-free combination. And the bulk theory is trivial and the boundary theory is anomaly-free, if the masses have the same sign. For the non-trivial theory, psi1 and psi2 have the opposite signs of the mass, so for either sign of epsilon, one of them has a boundary localized mode and one does not. So this is the interesting case where the bulk theory is non-trivial, and there's a single edge localized Majorana mode on the boundary. So what I've said until now, I think will be familiar to many of you because it's been important in recent condensed matter physics. And of course, it's been important in areas to which Shoucheng and Zhang made very important contributions. There's a small variant of this that might be less familiar. Let's consider the trivial theory with psi1 and psi2 having the same sign of m. But instead of flipping the mass, let's flip the sign of the boundary conditions for one of the fermions. Now, anomalies can depend on the boundary conditions in general. And we're going to see in a moment that in this case, anomalies do depend on the boundary conditions. Because so we're not guaranteed by any general consideration that this setup will be anomaly-free, and in fact it isn't. So to see this, you just note that flipping the boundary condition for one of the two fields has the same effect as flipping the mass for one of the two fields. It leads to a setup in which one of the two fermions, but not both, has a boundary localized mode. So if we flip the boundary condition, it will contribute to the anomaly. And this last statement might be slightly unfamiliar, but actually it's closely related to mean field theories of the Kondo effect. But I'm afraid I can't explain that right now, given the time. For the application to string theory, which I'll use the last 3 minutes to explain, I'm going to have to claim it's 3 minutes rather than 1, as our kind chairman has said. We need the following. Since anomalies do not depend on the masses, flipping the boundary condition contributes to the anomaly whether the fermion has a bare mass or not. In string theory, we'll be studying a similar problem, but with massless fermions. And I defined a discrete theta angle alpha, which is 0 or 1, by saying that the bulk partition function is -1 to the alpha zeta. So if alpha is 0, it's 1. If alpha is 1, it's -1 to the zeta. So alpha contributes to the anomaly if we're on a manifold with boundary. So let n be the number of boundary localized fermions, r the number of bulk fermions with a flipped boundary condition, and alpha the bulk theta angle. So I've derived a general condition for anomaly cancellation. N plus r plus alpha is even. So condensed matter physicist, well, in most applications, a condensed matter physicist, one wouldn't consider R, although one would in mean field theory of the Kondo system. But in SPT phases, people usually consider this formula for n and alpha only, but we can generalize it to include flipping the boundary condition, and then it has this general form. So now in the last 2 minutes, we'll turn to string theory. So string perturbation theory is defined by a path integral in a 2-manifold, which is the world sheet sigma of the string. The path integral describes a map from sigma to space-time. And in addition to bosons that describe the map, the world sheet path integral has 10 real non-chiral Majorana fermions that are related to the bosons by world sheet supersymmetry. So there are 2 string theories in which the world sheet is oriented, meaning there's no time reversal symmetry. And our discussion precisely applies. These 2 theories differ by a factor of -1 to the zeta. So starting with either type 2a or type 2b, and adding in the SPT phase associated with the Kitaev chain, we get the opposite string theory. Now let M be spacetime. A brane is a submanifold of spacetime in which strings are allowed to end. So when you draw this picture of a Riemann surface with boundary, you imagine that in bulk, the Riemann surface maps to anywhere in space-time, but on the boundary, it has to map to n. Now, if n is of codimension r in space-time, for example, if m is 4 dimensions and n is a cosmic string, then r would be 2. But if r is the difference in dimension between n and m, world sheet supersymmetry forces us to flip the boundary condition on r of the world sheet fermions. And as we know, that will contribute to the anomaly. Now, Polchinski considered branes with space-time supersymmetry. And these branes had even r for type 2b superstring theory and odd r for type 2a. Polchinski didn't consider the anomaly I'm discussing explicitly, but his theories were anomaly-free because they had r plus alpha equals 0. Alpha was 0 for type 2b and 1 for type 2a, and r was even or odd, as the case may be. So Polchinski's branes had r plus alpha equals 0. So he didn't consider this anomaly explicitly, but we can see he canceled it. Sen constructed non-supersymmetric branes where r plus alpha was not 0, as for Polchinski, but was 1 instead. His considerations also did not involve anomalies in a direct fashion, nor was his answer described in terms of a theory with an edge-localized fermion. But from our discussion, we know how to cancel an anomaly-free theory in the naively bad case where r plus alpha is 1. We add a boundary localized fermion so that n is 1. and then n plus r plus alpha is even again. And my claim, so Sen gave a clear and consistent but slightly baroque set of rules for calculations in the presence of a non-supersymmetric brane. My claim is that Sen's rules have simple explanations in the new language and have to do with the existence of an edge-localized Majorana mode on the boundary of the string world sheet. So there isn't time to explain everything, but if the chairman will give me another 30 seconds, I'll just say that when the string ends on a non-supersymmetric brane, the space of operators that can be inserted on the string world sheet endpoint is, according to Sen, twice as big as for a supersymmetric brane. So my interpretation is that you have the operators V that you would construct by ordinary rules, but there's an edge-localized fermion, so there are additional operators lambda V. And that accounts for that one of Sen's results. And his other results also have natural interpretations here. But I think I've prevailed upon our chairman long enough, so I'll stop here.
Thank you. So, any question?
Yeah, just a very quick question. So, well, we haven't mentioned the time inversal symmetric case, but actually with time inverse, we know that the original tenfold way classification has a Z classification for Kitaf chain, but only with the interaction reduced to Z8. I'm wondering whether your anomaly analysis can distinguish interacting and non-interacting systems at all.
Well, the anomaly only depends on n mod 8. Or I forgot if I called it n or r. But the anomaly depends on the number of flip or the number of boundary localized fermions mod 8 contributes to the anomaly. So the mod 8 periodicity has been known previously in string theory. The way it's usually said is that D-Branes have a K-theory classification. And K-theory, with time reversal symmetry, K-theory is mod 8. If you like, the continuation of my talk into the second sheet would kind of resolve that a little, refine that a little bit by explaining. So that mod 8 story has been discussed for supersymmetric D-Branes, but you can extend it to non-supersymmetric D-Branes by continuing in the spirit of this lecture. Anyway, yeah, you only see the number of boundary localized fermions mod 8 because the anomaly is mod 8. That's all I'll be able to say.
Okay, that's fine. Yeah, thanks.
Yes?
So you said that the case when you don't change the mass but change the boundary condition,
Yes.
and you mentioned the Canonical effect. I just want to say I think there is a simpler way to realize that in condensed matter, which means you consider a domain wall between two systems instead of a boundary,
Yes.
and the other side is like with a huge mass, and then changing the boundary condition without changing the mass is probably equivalent to changing the mass of the other side.
Yes.
So then in that sense, like the reason of the zero mode is really the same when you change the mass or change the boundary condition.
Yes. Okay, that's a reasonable argument.
The short question? If not, let's thank the speaker again.